The second processor scheduling method that we are going to consider is shortest process first, or shortly SPF. In this method, the processor is assigned to the process with the smallest execution processor burst time. This requires future knowledge of the execution time. In our examples, it is given as a table, but actually these burst times are not known by the operating system. So it makes prediction. One approach for this prediction is using the previous processor burst times for the processes in the ready queue, and then the algorithm selects the shortest predicted next processor burst time. We are considering again the same processes with the same timing for input and I/O. We are going to apply shortest process first for scheduling the CPU, but first come first served for the I/O device. At time 0, process A arrives. It enters the ready queue. Because ready queue is empty, it is deleted from the ready queue and it starts execution. This is showing what is the next CPU burst time. It is 4. Here for the processes in the ready queue, it is also mentioned what is the next CPU burst time, because the shortest one is going to be selected from the ready queue. Initially we have only process A, because of that it is selected for the execution. While A is executing, process B arrives at time 2. Then at time 3, process C arrives. Both of them are entered to the ready queue. The next CPU burst for B is 8, and the next CPU burst time for process C is 2. Then at time 4, process A finishes its first execution. It goes to the device queue. Because device is empty, it is immediately selected for the I/O operation. Meanwhile, the shortest process in the ready queue is chosen for execution. The processes in the ready queue were B and C, because the next CPU burst of process C is shorter than process B, it is chosen. C starts its execution. At time 6, while process A continuing its I/O operation, process C finishes its first execution and it goes to the device queue. Because there is a process doing I/O operation in the device, it will wait in the device queue. The only process in the ready queue is process B. It is chosen for the execution. At time 7, process D arrives. It enters the ready queue. Processor is busy with the process B. B continues its first execution. The first I/O operation of process A finishes. Process A enters to the ready queue. We have D and A in the ready queue having next CPU burst, 1 for D and 4 for the process A. At 9, process C finishes its I/O operation and enters again to the ready queue with next CPU burst time being 2. At 14, process B finishes its first execution. It goes to the device queue. It is immediately chosen for the I/O operation. This is the first I/O operation of process B. The process in the ready queue having the shortest next CPU burst is process D. It is chosen for execution. D starts its first execution. At 15, B finishes its first I/O operation. It enters the ready queue having next CPU burst time as 8. Meanwhile, the process D finishes its first execution. It enters to the device queue. It starts immediately the I/O operation. The process chosen for execution from the ready queue is process C, having next CPU burst time as 2. At 16, process D finishes its first I/O operation and enters the ready queue. Next CPU burst for process D is 1. At time 17, process finishes its second execution. This is the last execution for the process C. Process C terminates. The shortest one in the ready queue is process D. It is chosen for the execution. At time 18, D finishes its second execution, enters to the device queue, and starts its I/O operation. The shortest one in the ready queue is process A. A starts its second execution. Process D finishes its I/O operation. It enters the ready queue. process A finishes the second execution, it enters to the device queue. The shortest process in the ready queue is process D. It starts its third execution. At 23, process D completes its last execution, so process D terminates. We have only process B in the ready queue. It is chosen for execution. At 26, process A completes I/O operation, enters to the ready queue. At 31, process B finishes its second execution. Process B terminates. A is the only process in the ready queue. It is chosen for execution. This is the third execution of process A. At 35, process A terminates. Total time is again 35. All the time processor is busy, so processor utilization is 35 divided by 35 multiplied by 100. It is 100%. In real life, there will be context switch here. We ignored that. Because of that, processor utilization will be less than 100%. The throughput is the number of processes, which is 4, divided by the total time, which is 35. It is again 0.11. The turnaround time for process A starts at 0, terminates at 35. So turnaround time for process A is 35 minus 0. It is 35. The process B is submitted at 2. It terminates at 31. So the difference is 29. It is the turnaround time for process B. For process C, submission time is 3. Termination time is 17. The difference is 14. For process D, submission time is 7. Termination time is 23. The difference is 16. The turnaround time average is the average of these individual turnaround times. The average turnaround time for shortest process first is 23.5 now. Remember that it was 28.25 for first come, first served. Wait-in time for process A is 0 minus 0. Wait-in time for process A. Again, process A enters the ready queue 3 times. One of them is because A is submitted, and the next 2 is because A finishes its I/O operation. For the first one, it is immediately chosen for execution, so 0 minus 0. For the second one, the time it spends in the ready queue is 18 minus 8. And for the third one, it is 31 minus 26. So the total waiting time for process A is 15. For process B, the process B enters the ready queue 2 times. It waits there for 6 minus 2 for the first time and 23 minus 15 for the second time. So the total waiting time is 12 for the process B. The process C enters the ready queue at 3. It is chosen for execution at 4. The difference is 4 minus 3. Then it enters the ready queue at 9. It is chosen for execution at 15. 15 minus 9. The sum is 7. The process D enters the ready queue 3 times. It has 3 CPU bursts. It enters at 7, starts execution at 14. Then it enters at 16, starts execution at 17. The last time it enters at 19 and starts execution at 22. So we have 14 minus 7, 17 minus 16, and 22 minus 19. The sum of these terms is 11. The average waiting time calculated by considering all the waiting times is equal to 11.25. Notice that it is shorter than the average waiting time for the first come, first served. Response time is the time spent between the process submitted to the system and it starts first execution. The process A is submitted at 0. It starts immediately, so response time for process A is 0. B is submitted at 2, starts execution at 6. So the response time for B is 4. Process C is submitted at 3, starts execution at 4. The response time for C is 1. For the last process, D is submitted to the system at 7 and starts execution at 14. So response time is 14 minus 7, for process D, which is 7. The average response time for shortest process first is found as 3, which is shorter than the average response time for first come first served, which was found as 4.5. Now we are going to consider the processor scheduling algorithm called shortest remaining time first algorithm, shortly SR. This is the preemptive version of the shortest process first. The scheduling algorithms we discussed so far are all non-preemptive algorithms. That is, once a process grabs the processor, it keeps the processor until it terminates or it requires input-output. To deal with this problem, if so, preemptive algorithms are developed. In this type of algorithms, at some time instant, the process being executed is forced to preempt CPU in order to execute a new selected process. The preemption conditions are up to the algorithm design. Shortest process first algorithm can be modified to be preemptive as explained in the following. Assume that while one process is executing on the processor, another process arrives. The new process may have a predicted next CPU burst time. The new process may have a predicted next processor burst time shorter than what is left of the currently executing process. If the shortest process first algorithm is preemptive, the currently executing process will preempt the processor and the new process will start executing. The modified shortest process first algorithm is named as preemptive shortest process first or shortest remaining time first, shortly SRTF algorithm. Consider the process states. Start is the process has just arrived. Ready is the process is waiting to grab the processor. Running is process has been allocated by the processor. Waiting is the process is doing I/O work or blocked. Halted state is the process has finished and is about to leave the system. When the process starts, it enters the ready queue. It waits there until it is chosen for execution. And then while it is running, if there is an I/O request, it goes to the device queue, and when the I/O completed, it enters back to the ready queue again. After several cycles, when the process finishes all of these operations, it passes to the halted state and it terminates. Notice that a process enters the ready queue because it is just started or completed I/O operation. There is one more case for entering the ready queue, which is because of preemption. While a process is in the running state, if there is an interrupt and if that process is forced to leave the CPU, it is ready for the execution, but it is interrupted. Because of that, it goes back to the ready queue. The Gantt charts for CPU and I/O is given here. When the short remaining time first algorithm is used for scheduling the CPU. Again, first come first served is used for I/O as in the previous examples. At time 0, process A arrives, it enters the ready queue. Here it is shown that this is the process A, this is the next CPU burst, and this is the remaining time for the next CPU burst. As the process is executing, for the next time it enters to the ready queue, the remaining time will be updated. Because there is no other process in the ready queue, it is chosen for the execution. This is the first execution of the process A. At time 2, process B arrives and it enters to the ready queue. The remaining time is 8 for the process B. A continues its execution because when the process B is entered to the ready queue, the remaining time for process A is 4 minus 2, which is 2. It is smaller than the remaining time of the process B. At time 3, process C is submitted. Its remaining time is 2. The remaining time for process A is 1, so this is smaller, it continues its execution. At time 4, process A finishes its first execution and enters to the device queue. It starts immediately doing I/O operation. And the process in the ready queue having the shortest remaining time is process C. It has remaining time as 2 units. Process C is chosen and it starts its first execution. Then process C finishes its first execution. At time 6, it goes to the I/O device queue. It will wait there because A1 is already doing its I/O operation. It is not finished yet. In the ready queue, we have only process. In the ready queue, we have only process. In the ready queue, we have only process B, and it is chosen for execution. B starts its first execution. Then at time 7, process D arrives to the system. The remaining time for process D is 1, and the remaining time for the process B is 7 at this time. It has executed for 1 unit of time and the remaining time is 7. Because of that, there is a preemption. Process B preempts the CPU. It enters back to the ready queue and process D starts its first execution. At time 8, the preemption of process B is shown by this arrow at this point. This is showing that there is a preemption here. At time 8, process D finishes its first execution. It goes to the I/O device queue and process A enters to the ready queue. For the I/O device, the first one in the ready queue is process C, so it starts its I/O operation. In the ready queue, the shortest one is the process A, so process A is chosen for the execution. It starts to do second execution. At time 9, process C finishes its I/O operation and enters to the ready queue. When compared, the remaining time for process A is 3 units of time and the remaining time for C is 2. Because of that, there is preemption for process A. Process A enters to the ready queue and process C starts its second execution. At time 10, process D finishes its first I/O operation and enters to the ready queue. Compared to the remaining time of the process executing, which is process C, and the remaining time is 1, because they are the same, C continues its execution. There is no preemption at this point. Then at time 11, the second execution of process C finishes, so process C terminates and it leaves the system. The process having the shortest remaining time is process D. It starts its second execution. At time 12, the second execution of process D finishes. It goes to the device queue and immediately starts I/O operation. The process having the shortest remaining time is process A. At time 9, it was preempted, so it continues to the second execution. At time 13, process D finishes its I/O operation. It enters to ready queue. Its remaining time is shorter than the remaining time of the process A, which is 2. Because of that, process A is forced to preempt the CPU once more. It enters to the ready queue. Then process D starts its third execution. Now at time 14, the third execution of the process D finishes. It terminates and leaves the system. The process A is the one having the shortest remaining time in the ready queue, so it is chosen for execution. At time 16, process A finishes its second execution. It goes to the device queue and starts its I/O operation. We have only process B in the ready queue, so it continues its first execution. At 20, process A finishes its I/O operation. It enters to the ready queue because the remaining time for process B is 3. It is shorter than the remaining time of process A, so B continues its execution. At time 23, process B finishes its first execution and it enters to the device queue. And process A is chosen for execution. This is the third execution of the process A. At 24, process B finishes its I/O operation. It enters to the ready queue. At 27, process A finishes its third execution and it terminates. We have process B in the ready queue. It is chosen for execution. And when it finishes its second execution at 35, also the process B terminates. Therefore, all the processes are completed in 35 units of time. Again, always the processor is busy, so the processor utilization is 35 over 35 multiplied by 100, which is 100%. Throughput is totally we have 4 processes. They completed in 35 units of time, so the throughput is again 0.11. Turnaround time for process A is at 27 it terminates, it's 0 it was submitted, so it is 27. Similarly, the turnaround time for process B is 35 minus 2, it is 33. For process C, it is 11 minus 3, so 8. And for process D, it is 14 minus 7, so it is 7. The average turnaround time is found as 18.75 for the shortest remaining time. And notice that this is even shorter than the average turnaround time for shortest process first case. Process A entered to the ready queue several times. The first one is when process A submitted to the system. The second time when the process A finishes its I/O operation. Then the third time because of preemption. And here there is one more preemption. It enters to the ready queue 5 times. So the waiting time for process A is the summation of these 5 terms, which is equal to 7. Process B enters the ready queue 3 times, one for the submission. The second one is because of preemption, and the third time because it has completed the I/O operation. All these times are considered, so the waiting time for process B is found as 16. And similarly, process C enters to the ready queue here because of submission, it starts execution there. And another entrance is here, but it is chosen immediately for execution. It's causing a preemption on process A. When it is considered 4 minus 3 here, and here 9 minus 9, it is 0. So waiting time for process C is 1. The last one is process D, and it has very short execution time for each burst. Because of that, when it is submitted to the system, it causes preemption here on process B and start execution immediately. Here it enters to the ready queue because I/O operation is completed, but there is no preemption here because the remaining time of process C is same as the remaining time of process D. It waits in the ready queue until 11. And the last time here, it finishes I/O operation, enters to the ready queue. It causes preemption, so waiting time for the last entrance is 0. Total waiting time for process D is 1. Notice that the waiting time for process D is very short compared to the previous cases, and the waiting time for process B, which has long CPU bursts, is very long. Compared to the previous examples. The average waiting time is found as 6.25. It is shorter than the average waiting time of shortest process first. This is the algorithm having the shortest waiting time among all the algorithms. However, it is not possible to apply the shortest remaining time algorithm in practice. Instead of that, the remaining times are predicted. Response time for process A is 0. It is submitted and started execution immediately. The response time for process B is 6 minus 2, it is 4. For process C, it is found as 1, and for process D, it is 0. Average response time is 1.25, and it was 3 for shortest process first. Here, an example of shortest job first scheduling is given. We have 4 processes having execution time 8, 4, 4, 4. Part A is showing running 4 jobs in the original order. However, if the shortest job first algorithm is applied, then the ordering is shown in this figure. Notice that for the first come first served, while the shorter processes are waiting for a long process because they arrived later, in the shortest process first case, the process having the long CPU burst waits the others. Because of that, the waiting time, the turnaround time, and response time on the average is shorter than the first come first served algorithm.